Good. All right. So good morning, everybody, and welcome to the last segment of our meeting. And I'm very happy to introduce Ian Wood from the University of Kent. And he's going to speak about the spectrum of the Maxwell equations for flat interface between non-homogeneous dispersive media.
Okay, thank you, Christoph. Thank you, Jonathan, also for organizing this. This is joint work with Malcolm Brown and Michael Schmidt from Cardiff and Thomas Donau in Halle and Michael Plum in Karlsruhe. It's work that's been going on for a while, and I'll talk about various bits of it. Oops. What are we interested in? Obviously in electromagnetism, you do get various types of interface problems, right? These are things that people look at quite a bit. So you've got things photonic crystals, you've got waveguides, you've got so-called plasmonics. And often these involve materials where the permittivity is frequency dependent. So one model that comes up a lot, and I'll mention this later in the talk as well, is the so-called Drude model if you're modeling metals. And so then often these models are going to lead to non-self-adjoint problems. You've got complex valued frequency dependent coefficients, so that makes it a non-standard spectral problems. And what we do in this work is we have a very general dependence of the electric permittivity on the frequency or the spectral parameter. And what we want to do is we want to understand the spectral structure that we get from this kind of problem. So essentially we set out with time harmonic ansatz for the Maxwell equations. So I've just put that up here for everybody. So the thing is, so two of the parameters that come up in these frequently are the magnetic permeability. So that's this mu naught here. And we're not going to assume anything particular about that. That's just going to be constant. But what we are going to allow is the electric permittivity, this epsilon here, to be frequency dependent. And it's also going to be allowed to depend on the spatial variable, but we're only going to allow it to depend on one spatial dimension. So it only depends on the x1 direction. Right, and then we've got these divergence conditions in Maxwell's equations. So an example of the kind of situation we could be looking at would be the following. So we've got two half spaces, and in the left half space, we've got a metal, which we're modeling with this Drude model, where the epsilon then looks like this. And in the other half plane, we've just got a dielectric, which just has a constant electric permittivity. Right, so here, obviously, the x1 dependence is only going to depend on the half plane, but we will allow some more general dependence on x1 later, but this is the kind of setup that we're looking at. Right, so more generally, what are we going to assume on the epsilon? So we've got the two half spaces, and we're just going to call the epsilon in left half space epsilon minus, and in the right half space epsilon plus. And then we're going to assume this maybe slightly strange looking smoothness assumption on the epsilon plus and epsilon minus. So interfaces appear in this model essentially through discontinuities of the epsilon, right? So it's clear that if we want to have one interface at x1 equals 0, then we're going to want epsilon minus and epsilon plus to be somewhat smooth away from that interface, and the methods that we use are going to actually require this, the third derivative to be bounded. I'm not claiming that that's in any way optimal. That's just what comes up with the way we go about things. Right, And then it's possible that this function epsilon has singularities. So if I just go back to the previous slide, if you look at the Drude model here, then there are singularities in omega here. And so we'd want to exclude those. So that's what this d of epsilon does, right? We're just excluding singularities. So typically, like in that Drude model, it'll only be 2 points, right? But we certainly want to assume that obviously the d of epsilon is a non-empty set. Right, and in this setting, we have typically an interface at x1 is equal to 0 because we're going to have some kind of jump at that point. Okay, and so at least show you some picture. I've got this one here. So this shows the kind of thing that we're looking at, right? So we've got a crystal on the left, and then on the right, we've got a vacuum in this picture, and you can see you've got some light here in the crystal. And there's essentially two different things then going on. You've got a surface wave here, and then you've got some of the light which is traveling off, basically orthogonal to the surface away from it. All right, now this picture is a bit of a cheat because there is a waveguide on the left-hand side, and in our situation, because we don't allow the epsilon to depend on x2 and x3, we're not going to have a waveguide on the left, but it's well, the nicest picture I could find, and it sort of illustrates the kind of effects we're going to be looking at. Okay, so now the light here along the surface is often called a surface plasmon, right? These are well, the physicists study these a lot, so there's a lot in the physics literature. There's not so much in the maths literature on these, and so well, I've now got a list of some results for more general, just non-self-adjoint Maxwell problems. Right, so generally looking at this plasmon problem with a linear spectral parameter, there's work by Grieser back in 2014, and then well, I'm citing one particular Amari work, but the group around Amari have done more work on this, or these kind of problems. Moving away, not necessarily looking at interface problems, but looking at the spectrum for non-self-adjoint Maxwell problems. There's an early work by Lassas on a bounded domain. This was then looked at for unbounded domains in Alberti et al. In 2019. And then there's more work by Bergli, Ferreresso, Maletta, and Tretter on this more recently. In these kind of problems, you can, well, in some situations, it's going to turn into a problem where you've got a rational dependence on the spectral parameter. So these are studies, and in this Maxwell setting, this is something that Engström has done. There's a few papers by him. And if you look in particular at the Drude model, then there's a load more work on that. So the group around Joly, in particular, I'm citing Cassier, Hazard, and Joly have worked on this. There's more work by Ferreresso and Maletta, and also more work by Engström on the Drude model in this kind of setting. Okay, so let's look at the maths that we're actually going to be looking at. So we're going to turn it into a second order problem for the electric field. All right, so we've got the curl of E minus omega squared epsilon E is equal to the right-hand side, or 0, right? And we need the divergence of epsilon times E to vanish. All right, so now the epsilon depends on omega in a fairly general way. So this is by no means a sort of standard eigenvalue problem. And so what we're going to do is we're going to look at an operator pencil, or if you prefer, maybe think of it, a family of operators that depend on this parameter omega. Right, and so the operator L of omega is just curl minus omega squared epsilon. All right, the underlying space is L2 of R3 with values in C3 here. And the domain that we look at is the functions in this L2 space, such that curl and the curl again lie in the L2 space. And we have the divergence condition epsilon times E is 0. All right, so now if we look at the operator with this domain, if we think about its range, right, so if we apply the L of omega to the field E, then of course there's the curl term, which will have divergence 0, and there's the term with the epsilon times E, which is also divergence free. So we need to, as a codomain, we want to look at the space where the functions are divergence free. Okay, now, so we've now got an operator acting essentially from this domain into the codomain here. We've got a family of operators, and so we have to say what we mean by the spectrum here, but this luckily came up in Monica's talk with the show complement yesterday. We're going to do the same thing here. So we say that omega is in the resolvent set of the operator pencil if 0 is in the resolvent set of the operator L of omega for the fixed omega. Right, and we can define the various parts of the spectrum in the same way here. So the spectrum just consists of those omega such that 0 is in the spectrum of L of omega. We have an eigenvalue of the pencil if 0 is an eigenvalue of the operator L of omega. And omega is in the Weyl spectrum of the pencil if 0 is in the Weyl spectrum of L of omega, which means you've got a sequence of functions in the domain which have norm 1, which converge weakly to 0, and such that in norm L of omega applied to the sequence goes to 0. Okay, so we said that we're not going to allow any explicit x2 and x3 dependence in our problem. So the natural thing to do is to use the Fourier transform to get rid of the differentiation in those directions. So that's what we're going to do. Right, so k is now in C2. And well, our variables are now going to be x1, k2, and k3. And we have this gradient k at the top here, and then obviously we need to express the curl in the new variables. So we have the curl k is this, and then the operator that appears in our equations is the curl k of the curl k, which is this matrix differential operator that you can see here. Right, and so then in the Fourier variables, we're going to call the operator L hat. So we then have an operator L hat of omega, which is this curl k minus omega squared epsilon. And notation-wise, I'm now going to, in the Fourier variables, I'm going to call the functions u rather than e. So the e was the electric field in the original variables. Now that I've done Fourier transforms in 2, I'm going to call the function u. Right. Now, well, a lot of people working with Maxwell will know that one often then likes to look at what are called TE and TM modes. And so we're going to do another transformation, which essentially does that. Right. So rather than looking at the functions u1, u2, and u3, we're going to mix up the u2 and the u3 in this way given here, so that they become a v and a w. And so the advantage of that is that then our Maxwell problem turns into Sturm-Liouville problems. So I don't expect you to take in all the details here. The right-hand sides are not important, right? That's just the right-hand side, how the right-hand sides transform. The important thing is that on the left, now for this V, so this is some linear combination of U2 and U3, we have a Sturm-Liouville type problem, right? And for the W, for the other components, you've got a simpler Sturm-Liouville type problem here. And if we can solve these, then we can recover the third component, the U1, from this formula at the bottom, which involves the V prime. Right, and so if we do this transformation, we obviously also have to look at what happens with the domain. And so you've got that at the bottom here. And that also nicely decouples the V and the W components. So if you look at this, then all the conditions might involve V and U1, or they involve W, but they don't involve all three at any point. Now, the domain looks a bit different here. So originally for the E field, I required that the curl, well, the E itself, its curl and the curl lie in L2 of the whole space. So I'm writing that in a different way here. So I'm requiring that this is essentially after the transformation, what are the components of the curl and the components of the curl lie in L2 of half spaces. And then to make sure that they end up in L2 of the whole space, we have jump conditions. So that's what this bottom line with the double brackets is meant to indicate. These are meant to indicate the jump of these functions across the interface has to vanish. So this is going to be the jump in the sense of trace, ultimately. And then you've additionally got this divergence condition here at the end of the second line. Right, so that's what the domain looks like. Now, we can now formulate results for this. Essentially, they are going to depend on properties of the fundamental systems for the Sturm-Liouville problems in blue here for the V and the W. Now, for the fully general case, it involves a whole lot of assumptions that you might be able to check in concrete situations, but I'm not going to list all of those for you here. So what I'm going to talk about today is I'm going to have a look at the case when the epsilon in each of the half planes is periodic, because then we can formulate the results a bit more easily. And then I'll also look at the case when actually the epsilon in both half planes doesn't depend at all on the x1 variable. So we're back to actually the example I had at the start, where you have one material in one half space, a different material in the other half space, but they're homogeneous materials in the different half spaces. Okay, so I need to introduce just a bit of notation and concepts relating to the periodic case. So we've got Sturm-Liouville equations of this type here. So I'm just writing the coefficients as P and Q here. Right, so these, well, you can write then the canonical fundamental system for this problem is the solution to this matrix problem here. And we're fixing initial conditions at 0, like this. Now, if we have periodic coefficients, then the growth of the solutions can be characterized in terms of what's called the monodromy matrix. So that's evaluating this system of fundamental system here after one period. So at phi of A. And in particular, if we're interested in the growth or decay properties of this, then we're going to be interested in the eigenvalues of the phi of A. And because the determinant is 1, these are controlled essentially by the discriminant. So this discriminant D is going to pop up in the conditions that we're going to see later, and that's going to be the trace of the monodromy matrix. Right, and so if this discriminant is not either plus or minus 2, then we get two distinct eigenvalues, which we can write as e to the kappa A and e to the minus kappa A, right, where we choose the real part of kappa to be greater or equal to 0. And if d is not in minus 2, 2, not in the full interval minus 2, 2, then we can choose the real part of kappa to be greater than 0. So in that case, we have one eigenvalue that's modulus greater than 1 and one eigenvalue that's modulus less than 1, which leads to one growing and one decaying solution. So that's going to play a role in a moment. Okay, so let's go back to our Sturm-Liouville problems. So for V, we had this problem that we've got in the third line here. Right, so now I'm going to assume that epsilon plus is A plus and epsilon minus is A minus periodic. A plus and A minus don't have to be the same. And so then we're going to have in both half spaces, there's going to be a discriminant associated with this this Sturm-Liouville problem, which we denote by dv plus or minus of k. And then we also have this little d of k, right? And this is something like a Wronskian. Right, that we get from this problem. Now, I'm just saying here for suitable fundamental systems. So in the case when the discriminant is outside of minus 2, 2, then this V1 minus is going to be the solution that decays at minus infinity, and the V2 plus is going to be the solution that decays at plus infinity. So this is a condition that depends then in that case on the two decaying solutions in the different half planes, and it's somehow coupling these two. Right, and then we have the same things for the W problem, just that this is a simpler Sturm-Liouville problem, and so it looks a little bit easier. But again, we get the discriminants dW plus minus, and maybe we should have called this dWk rather than d tilde k, but this d tilde k is this this Wronskian type determinant involving the decaying solutions. Okay, so now let's get round to some results. So first of all, I'm going to start with the resolvent set. So if so we first have to exclude a set that we actually haven't looked into in detail, that we can't treat at the moment, or can't say anything about at the moment. And so this consists of the omegas where essentially this function omega squared epsilon gets arbitrarily close to the positive real axis. So we have to exclude that. All right. So now if we know that for all k in R2, the discriminants for the V problem and the W problem in both half planes are not in minus 2, 2. And the two Wronskian type quantities, the d and the d tilde, are not equal to 0. And then there's an additional condition here on the epsilons, or combinations of the epsilons at the interface. So if all of that is satisfied, then we know that we're in the resolvent set. Okay, so I'll try and at least give you some idea of what we do here. So what we do, we first, for the fixed k, we solve the Sturm-Liouville problems for V and W. Right, and obviously need to make sure that the divergence and the interface conditions are satisfied. And the non-vanishing of these Wronskian determinants means that you're going to get a unique solution to those problems. Right, so the non-vanishing of the Wronskian determinant effectively means you cannot connect up the decaying solutions from each side at the interface. Right, so that's basically a 1D problem, and then we need to basically go back and invert the Fourier transform in the k variables. And so that's going to require us to know things about how various quantities grow or decay in k. And that's where these conditions at the end, if I just go back to the previous slide on the epsilon that maybe appear a bit out of the blue here, they play a role there. So they guarantee that the k dependence is such that we can invert the Fourier transform and get back to solutions in the whole space. Right. So what about spectrum? So we've got different types of spectrum. So the first type of spectrum is essentially going to come from the case when the Wronskian vanishes. Right, so I now just need one K0 in the plane where both of the discriminants are outside of -2,2. So we've got decaying solutions in each half plane, and the determinant vanishes so we can match them up at the interface. We also have this assumption here that this omega squared epsilon plus or minus doesn't get close to K0 squared, essentially. So if we have that, or we've got corresponding conditions for the problem for W, then we are in the Weyl spectrum of the pencil. Right, so what do we do here? So for the fixed K0, we now have a non-trivial eigenfunction. So that's what this determinant condition guarantees. We can then use smooth cutoffs in the x2, x3, or the k2, k3 variables that move off to infinity in that direction. So that means it's moving along the interface. It's all a bit technically involved because we need to make sure that the interface and divergence conditions are still satisfied, but this whole thing works. So from essentially the one-dimensional eigenfunction, we can generate something that gives us a Weyl sequence for the three-dimensional problem. Right, then we also have radiation in x1 direction away from the interface. So this comes from the case when the discriminants are in the interval -2, 2. Yeah, so another spectral result, we can see that we've got no eigenvalues of finite multiplicity in this situation. So what's the idea here? So we take a bounded solution. So the fact that the discriminant is in -2, 2 gives us bounded solutions, at least in one of the half planes, either for the V or the W problem. We take that, we can cut it off smoothly in the x2 and the x3 direction, and then have the support moving off to infinity in the x1 direction. So in this case, we're away from the interface, so we don't have to worry about interface conditions and things like that then, but this gives us more Weyl sequences. Right, and the eigenvalue property just comes from shift invariance in the x2, x3 direction. So if we did have an eigenfunction, then we could shift in the x2, x3 direction, and we'd get an infinite set of eigenfunctions. Right, so see, time's running out. So maybe just, so this is the case for constant coefficients. So in this case, it's obviously you can write down more explicitly what the discriminant and the Wronskians are, and so you can more easily formulate the result, and so you don't have to explicitly write down discriminants and determinants anymore. You can write it out like this, but yeah, I'll maybe not say anything more about that. I was going to show you at least a picture, but maybe I'll just put the picture up. So for a more toy problem, this is a one-dimensional one where we don't actually, essentially we don't invert the Fourier transform. If you look at the interface between a Drude model and a dielectric, you can actually compute these different sets here, and so you can see them here in these plots for this particular example. So I think my time's up, so I'd better stop at this point, and thank you for your attention.
Thank you so much. Super quick question, maybe. Oh, I need to stop recording.